So section 1.2 is all about limits. How do we find limits and what are they exactly? So before we start out, let's look at a very simple example. We want to consider the function f of x equals x cubed minus 1 divided by x minus 1. So one thing that's important to note is that f of x does not exist at x equals 1. So why would that be the case? Well, what happens if you tried to plug in a 1 into this function? You would get 1 cubed minus 1 divided by 1 minus 1, which would be 1 minus 1 over 1 minus 1, which is 0 over 0. And that is a problem. So this actually represents itself as a hole in our graph. But we can talk about this function as a graph, and we can talk about the function for values other than 1. So let's take a look at what the graph looks like for values other than 1. So I've plugged in some coordinates, plugged in some values of x into the function, negative 1, 0, 1, 2, and 3. And these are the y values that I got. For negative 1, I got a 1. For 0, I got a 1. For 1, we know that it does not exist. If you see me write that D and E, that's what that means. For 2, we'll get a 7. And for 3, we'll get a 13. And then we'll put that on our graph. And you can see that I added a couple of extra points just to fill in the picture here. But the graph looks something like this. Now, what does the graph look like at x equals 1? We see a hole. It looks like it's approximately at the y value of 3, and we see a line that's approaching that hole on either side. So let's talk about what happens to f of x as x gets closer and closer to 1 from the left and from the right, and we're going to do this numerically. So I'm just going to calculate f of x, remember that's x cubed minus 1 divided by x minus 1, for all of these values of x. And as I filled in these values, you can see that as x gets closer and closer to 1 from the left, it looks like we're increasing, and we're getting really, really close to y equals 3. Notice I've got a 2.3, 2.7, 2.970 up to 3. And when I come from the other side, from the right, I'm starting at this 3.8 and I'm going down towards 3. So we say that as x gets closer to 1 from either side, f of x gets closer to 3. Now another way to write this is that the limit as x approaches 1 of x cubed minus 1 divided by x minus 1 is equal to 3. Now this doesn't necessarily mean that x cubed minus 1 divided by x minus 1 equals 3. In fact, in this case, there is no value of x that's going to give you an exact 3 for this function. But it does mean that as x gets closer and closer to 1, f of x gets closer and closer to 3. So this is what is known as the informal definition of a limit. If f of x becomes arbitrarily close to a single number L would be our 3, as x approaches c from either side, c would be our 1, then the limit of f of x as x approaches c is L. And this is written, the limit as x approaches c of f of x equals L. That's how you read that mathematical statement. So we're going to take a look at a very simple example. This is f of x equals negative 1 if x is not equal to 3, and 1 if x is equal to 3. And we're going to find the limit as x approaches 3 of f of x based on this informal definition here. So, if you try to fill in your chart, it would look something like this. So according to the definition of this piecewise function, if x is anything other than 3, the answer is negative 1. So notice I've got values that are on either side of 3. The 3 is going to be a 1, but everything else is going to be a negative 1. So we'll see what that looks like graphically. Now you can see from the graph and the chart, as x approaches 3 from either side, f of x is arbitrarily close to y equals -1. The value of a limit is always the y value. So the limit here, as x approaches 3 of f of x, is actually equal to -1, even though f of 3 is actually equal to 1. In some cases, the value of f doesn't matter if the line is not approaching that value from either side of x. So if you look at the graph, as we come in towards x equals 3 from the left, it's approaching this empty circle here at -1, and the same thing on the right. So this means that even though f of 3 is equal to 1, the limit as x approaches 3 of f of x is equal to -1. So this example illustrates a very important point. It is not necessary that the limit as x approaches c of f of x be equal to f of c. Okay, next we're going to talk about some cases in which a limit doesn't actually exist. Now, one of the first and one of the most basic kind is where the limit or the function approaches different values from either side. And remember, it said that in the informal definition that f of x had to approach or become arbitrarily close to L as x approaches c from either side. That's a single L. So if we can't find a single L, then the limit doesn't exist. So this is the absolute value of x divided by x is our function. And before we talk about this one, let's kind of review a little bit of what we know about the absolute value of x. The definition of the absolute value of x, most of you probably learned it as the idea that it makes whatever your value is positive, but it's actually a little bit more involved than that. The absolute value of x actually measures the distance from 0 that x is. So 3 is 3 units from 0, but -3 is also 3 units from 0. Now when you're talking about this algebraically, if x is greater than or equal to 0, the absolute value of x just has the face value of x, whatever it is. So the absolute value of 3 is 3. However, if x is negative, if you have something like -3, you could turn it positive by making that the negative of whatever that value is. So the absolute value of 3 is just 3 because 3 is positive. The absolute value of -3 you could write as -3, which would turn it positive. So this is an algebraic way to define the absolute value of x as a piecewise function. So the reason we want to do that is because we need to talk about the absolute value of x divided by x. So f of x is the absolute value of x divided by x, which we can split up into a piecewise function. So if x is greater than or equal to 0, then the numerator here is just x over x. And if x is less than 0, the numerator is -x. So when you simplify this, you get that f of x is equal to 1 if x is greater than or equal to 0, and -1 if x is less than 0. So we'll graph that and see what it looks like. So this is a sketch of what the graph of this function looks like. Now, as x approaches 0 from the left, we say that f of x approaches -1, and you can see that coming in from this side. F of x is approaching -1. But as x approaches 0 from the right, what is our f of x approaching? If you look at it from the right, it's approaching +1. Okay, so because f of x approaches two different values on either side of x equals 0, we say that the limit as x approaches 0 of f of x does not exist. Now you can talk about the limit of this function as x approaches any other value. For example, if you wanted to talk about it as x approaches 2, you could say, well, the limit from the left is 2 and the limit from the right is, the limit from the left is 1 and the limit from the right of 2 is 1. So it's approaching the same value from both sides, so therefore the limit as x approaches 2 is 1. But the limit as x approaches 0 for this function does not exist. Another example would be when a function is unbounded at a given value of x. So let's say we have the function f of x equals 1 over x squared, and we want to find the limit as x approaches 0 of 1 over x squared. So I'm just going to pull a graph from Google. You can just type in graph f of x equals 1 over x squared, and it will present you with something like this. Now, what can we say about f of x as x approaches 0 from the left? What about the right? Well, as x approaches 0, it looks like f of x is getting larger and larger and larger. And if you pulled up your graph and zoomed out on that, you would see that. So as x approaches 0, we say that f of x increases without bounds. So it's growing forever. It's never going to stop growing. So in this case, we say for now that the limit as x approaches 0 of f of x does not exist. Now later on in this chapter, we will talk about how to deal with this type of situation when you have a function that's increasing or decreasing without bounds. But for now, we're just going to say that this one doesn't exist, according to the definition. Another case where a limit may not exist is when the value of f of x oscillates between two values and never can settle on an L that it's actually approaching. So this example is the limit as x approaches 0 of sine of 1 over x. I want to be clear, this is not sine of x. Sine of x has a graph that looks something like this. I'm just going to give you a rough sketch of it. It makes this curve that repeats. Now, if we're talking about sine of x as x approaches 0, that has an actual value. The limit as x approaches 0 of sine of x is just going to be 0. We're specifically talking about the limit as x approaches 0 of sine of 1 over x. So if you tried to grab a graph of this function or to sketch it, on Google it looks like this. It's kind of crazy. But what actually is happening here in all of this kind of blue cloud that you have in the middle is that you're seeing this oscillating pattern getting closer and closer and closer to each other. So for example, if I tried to sketch it, I might have some wide oscillations out here, but they're getting narrower and narrower and narrower to the point where I can't even draw how close together they're getting. Okay, and then it kind of widens back out as we get further away from 0. So they're getting so close together in here that you can't see it, but it's repeating the same pattern over and over as x gets closer and closer to 0. But f of x does not approach a single value. If you get a step closer, you're going to go back between 1 and -1 again. So it doesn't approach a single L. So in this case, the limit as x approaches 0 of sine of 1 over x does not exist. So if you're ever trying to evaluate a limit and you want to see if it exists or not, probably the most basic way to approach this is what we've shown in this video. If you're going back to the basics, you might want to try filling out a chart with values of x that are around the value of your c, or you might want to try sketching a graph of it and looking what happens graphically. We'll talk in 1.3 about a way to do this a little bit more analytically. Sometimes it's just as easy as plugging in a point, but there are some conditions that have to be met before you can do that. So this is the most back to basics way to evaluate a limit.